in this presentation, I want to look at these two aspects. This one over here, describe the production of an induced EMF by a time-changing magnetic flux. We're going to discuss that concept. Now that directly relates to this idea of Faraday's law, which it looks at a formula where you can relate this idea of a time-changing flux to the induced EMF. So this Faraday's law is a formula that relates these two things, and Lenz's law gives an idea of the direction of the induced EMF. In which direction will the current actually flow to produce in response to this time-changing magnetic flux. So to start off, I'd like to bring in our FET application. I'm going to use this one. Now, in this case over here, we have a magnet. As you can see, we have this magnet, but it's not moving. So there is a magnetic field, and the magnetic field is going through. It's not difficult. It's not easy for me to draw this because it's the screen is black, and so it's not easy for me to show it. But we have got a magnetic field. We've got this magnet over here. It's producing a magnetic field, and this magnetic field is going through. It is actually going through this coil, but there is no induced EMF. And the reason for this is that there's only going to be an induced EMF when this magnetic field is changing. And the faster the change, the greater the induced magnetic field. And this is what this application shows us. So we switch on the water here, and we get now the magnet rotating, and as you can see, we're getting an induced magnetic field. So we're getting a changing magnetic field, and the slower the changing magnetic field leads to a slowing down or the lessening of the induced EMF. As I speed it up, we can see there that the induced EMF is much greater, as that we've got more energy that has been produced in our light bulb, and we can see that the movement here is much greater. It's interesting to see the to and fro movement. We're getting to and fro movement. Let me use another color here. We're getting a to and fro movement here. And this is going to come into our next section when we look at alternating current. Often these forms of producing an electric current will produce an alternating current, a to and fro movement. So Faraday actually quantified this, and we're going to look at that now. Let's slow this down, and when you slow it, you see it stopped altogether because we've got no changing magnetic field. So this is that idea over here, that to get an induced EMF, we need the magnetic flux to be changing. Now, what Faraday said was that the induced EMF, the E, is equal to, if there is one coil, it would equal to the change in phi over the change in T. So if you've got a single loop situation, you would have that. If you've got multiple loops, then it would be N, change in phi over change of T. And this is a rate of change. So the greater the rate of change of magnetic flux, the greater the EMF, and the more turns that you have, the greater the EMF. So this over here is your EMF, and this is basically your rate of change in flux linkage. So this is Faraday's law over here, and you need to, it is described by that formula. Now I want to spend a little bit of time now looking at Lenz's law, and to do that I'm going to use the PowerPoint that we have for this section. I'm going to bring it up over here. This is Lenz's law. So as it states here, Faraday's law tells us the size of the induced EMF, but we can find its direction using Lenz's law. And this over here is Lenz's law, so you perhaps want to write this down in your notes. The direction of the induced EMF is such that it will oppose the change in the flux that is producing it. Now, looking at this, I'm going to just go down to this diagram over here. As you can see here, we have got a north magnet moving in. So the north magnet is moving in, so it's creating an increase of flux of magnetic field from your north. So your north, your magnetic field is going like that. The direction of the current, you can see the direction of the current there is in that direction. If we use our right hand solenoid rule, where we put our fingers in the direction of the current, the thumb will point in the direction of the north. So we put our fingers in the direction of the current. Can we see here that we are getting a magnetic field being produced in that direction there, which is opposing here, opposing the change. We're getting an increase from that direction, so our induced EMF, our induced current is so that it sends it in the other direction. In this diagram over here, we're getting a lessening. We're having a movement away, and so the direction of the current, the induced current, will be such that it will produce a magnetic field in this direction. So using our right hand rule, putting our fingers in the direction, we see that our current is going to be in this direction. So this is the basis of Lenz's law that you will be discussing.